Okay, good morning if it's morning where you are. So today we're going to start a new topic, which is the continuous Fourier transform. Okay, which of course we're going to abbreviate as CCFT, analogously to the CDFT, which we just finished talking about. And so you remember that our way of doing this, our naming convention, the first thing here refers to time. So this means continuous time, and this means continuous frequency, as opposed to the CDFT, which had continuous time and discrete frequency. Okay, and the discrete frequency for the CDFT resulted in the fact that we had periodicity in time. So here we're not going to enforce periodicity in time. So that's why we have not a discrete set of frequencies. So we have aperiodic signals. And so we get the CCFT. And so when we first started talking about Fourier transforms a while back, we by analogy to the CDFT, we talked about the CCFT. And so the formula for the CDFT, remember, was okay. Like so. All right, and so the continuous time, not necessarily periodic analog of this is going to be that we're going to replace the discrete frequency n over t with a continuous frequency variable nu, and then the integral here will go from minus infinity to infinity. Okay. Like so. Okay. All right. So the first thing we should decide on is what's the domain of the CCFT. Certainly not any signal f is going to work, or even any continuous signal f. And clearly in exactly the same way as for the CDFT, the way we decided on the domain of the CDFT was we asked that the integrand be in L1. Okay. And because this has magnitude 1, that amounted to this being in L1 over a period, and the same argument holds here. And so the domain is just L1 on R. Okay. So note that the domain of the CCFT is L1. Okay. All right, so we're not going to worry right now about what the codomain is. So in other words, as a function of nu, what property does the CCFT have? We'll see that again, it's rather analogous to what we saw with the CDFT. But instead, to start out, let's just maybe look at a couple examples of CCFTs. And when I teach this course, or when I taught this course, I didn't make much of the sort of computational part of the course, but there's some interesting examples nonetheless that are worth looking at. Okay. Right. So let's first let's look at a signal which looks like this. So from A to A, it has the value 1 and then 0 outside. Okay. All right, so this is a simple computation that I'm not going to spell out the details of. It's hardly worth dwelling on it because an elementary computation gives you this. But I am interested in what the answer is. Okay, so it turns out that this thing is going to be important for us, and we're going to call this thing the continuous Dirichlet kernel. And what's interesting here is that if you recall, we did this in the discrete time case, sorry, in the periodic case. In the periodic version. So what did we have then? We had, so we're talking about periodic things. So here we go from minus t over 2 to t over 2. So that places a restriction on what the a's can be. Okay, but we can do the same kind of a thing. Okay, and then in that case, we determined that the CDFT of f was equal to the sampled periodic Dirichlet kernel. Okay, and so the point is the Dirichlet kernel seems to be connected to this particular kind of signal, which is one on some symmetric interval around 0. So here's the periodic version, here's the aperiodic version. And then the Fourier transform, be it the continuous time, continuous frequency, or the continuous time discrete frequency one, seems to be connected to the Dirichlet kernel. Okay, so I just want to kind of point that out, and we'll talk about a little bit more systematically about some things related to this later on. And again, by means of and so just to be clear here, the value there is 1. Similarly here, we're going to get to value 1. And we're going to look now not at a function which is constant on the interval minus a to a, but behaves like this little hat function. And again, you can do this interval explicitly. You know, it's slightly tedious. But what do you get out? So I care only about the answer here. Okay, so you get out a thing like this. And this, it turns out, is, as we will see, is what's called the continuous Fourier kernel. Sorry, the aperiodic Fourier kernel, or the continuous Fourier kernel, as opposed to the periodic discrete time, discrete version of it that we saw before. Okay. And so again, we had the continuous time analog. And we looked at the CDFT in this case. Okay, and so the function f here, it's entirely analogous. From A, let's say, and so again, there's some restrictions on what A can be. The idea is the same. And then what we calculated was that the CDFT of f in this case was the sampled Fourier kernel. Is there? Okay. All right, so the Fourier kernel seems to be connected to a signal that looks like this, okay, both in the continuous time case and in the discrete time case. Sorry, I apologize, both in the aperiodic case and in the periodic case, all right? Okay, good. Let's look at another example that illustrates something else, okay? This one we're going to calculate because it's kind of a fun calculation to do. And it's not always computed properly. All right, so we're going to take f of t to be a Gaussian function. Like so. Okay, so a here is a positive real number. Although you can take it to be a complex number with positive real part, but for simplicity, let's just do this. Okay, so let's compute the CCFT of this Gaussian function. Right? And so just by definition, it's that. Okay, so what I'm going to do, of course, is I'm going to combine the exponentials here, and then I'm going to complete the square. Okay, so I'm going to, as a function of t, I'm going to write this. So this is a quadratic plus a linear, and I'm going to add and subtract in the exponent a constant term in t that makes a complete square there. So let me not say any more about it. Let me just write down the answer. Okay, so that's the constant term in t that pulls out. And then you get e to the minus a. T plus I, and it's pi nu over a squared dt. Okay, so you can just directly verify that these two things are equal just by direct computation. All right, so so this is the integral that we're going to do. All right, and what we're going to do is we're going to recognize that this thing is the integral in the complex plane, because this thing here is a complex number, so we're going to sort of take that to be z, and we're going to notice that in the z plane it's an integral we're over a line with imaginary part equal to that, and we're integrating over the real part. Okay. All right. And so this is the line integral in C of function. Z goes to e to the minus a z squared with along the line. Okay, and the line is, so this is the real part of z. This is the imaginary part of z. Okay, and so let's consider the case where nu is positive for the moment. Okay, and then when nu is positive, this thing will be positive, and so the line is going to be positive, the upper half plane. Right? So the line is going to be this line here, and then this value here is pi nu over a. Okay, and then for nu negative, of course, it's going to be in the lower half plane. Okay, good. So that's the integral that we're going to evaluate. All right. And first we're going to, by a trick, convert that into just a regular sort of real integral that we will be able to calculate. And here's how we're going to do that. We're going to choose some capital R positive. And then I'm going to make a contour in the complex plane. Right, and so the contour is going to be like so. All right, so I'm going to take this line that I have here, and then at R, so this is minus R here, and R here. Okay, and so the contour is going to just be this box here, like so. Okay. All right. And so what I'm going to do is I'm going to now integrate, do a contour integral of this function around this contour. All right. And let me call this thing gamma R. Okay, so then, all right, so the first thing I notice is that if I'm going to do the integral of this function around this contour, the result will necessarily be 0 by Cauchy's theorem, because this function is holomorphic. Okay, so by oops. Cauchy's theorem. Okay, 0 is equal to the integral around this closed contour, e to the minus a z squared dz, and then what I'm going to do is I'm going to break the contour up into its segments, okay, along each of the 4 sort of edges of the rectangle. All right. So along the lower part of the rectangle, so from here to here, I'm integrating from minus R to R, and then E, and then along the that contour, the real part of Z is X, which is goes from minus R to R, and the imaginary part Y is equal to 0. So this is just e to the minus a x squared dx. All right. Then I'm going to integrate along this segment. Okay. So the interval from 0 to pi nu over a. Okay, and it's e to the minus, okay, a, and now x there is equal to capital R, and y is, well, it's going from 0 to pi nu over a, so plus I y squared dy. And then similarly, I get the, let me write in the this branch first, okay, because it looks kind of the same. So it's going to be the integral from pi nu to 0 e to the minus a r plus I y squared dy. And then finally, I get the top bit, which is the integral from r to minus r e to the minus a x plus, and then the imaginary part here is pi nu over a squared dx, right? Okay, and so the point is that this is the thing, more or less, that we're calculating, right? Except I replaced t with x, okay? And so I'm going to evaluate all the other stuff, the other 3 components here. All right. So let's look at the vertical integrals first. Okay, so note that e to the minus a r plus I y squared is less than or equal to. So let me spell it out first. So it's e to the minus a r squared, and then I have e to the minus 2a I r y. Okay, so that's the cross term in the product, and then I have e to the a y squared. Okay, and this is less than or equal to e to the minus a r squared, and then the modulus of this, so all of this business up here is real, so it's imaginary. So the point is the modulus of that is equal to 1. And then here y lies between 0 and pi nu over a, or pi nu over a and 0. And so it's going to be the worst case scenario here is going to be e to the a pi right, so it's going to be pi squared nu squared over a squared. The a is going to cancel, so it's going to be e to the pi squared nu squared over a. Okay. All right. And so therefore, okay, so that gives a bound on the integrand here. Okay, it's bounded like this. And the point is that as a function of, this integrand is uniformly bounded by this thing. Okay, and notice that this is uniformly bounded in R by 1. Okay, and so therefore, by the dominated convergence theorem, okay. All right, the limit as r goes to infinity of, so let me do the right vertical integral. So the integral from 0 to pi nu over a, e to the minus a r plus I pi a, oh, sorry, y. Squared. Okay, so sorry, I should really say this is for y in 0 to pi nu over a. Okay, good, because that's what this integral is concerned with. So dy is equal to the integral from 0 to pi nu over a, limit as r goes to infinity, e to the minus a r plus iy squared dy. And so the imaginary part here is bounded. That's what the whole business, the whole business here was about. And so the point is that this will go to 0 as r goes to infinity. Okay. All right, good. And so this shows that as r goes to infinity, this and this go to 0. Okay. And so what I get, therefore, is that this is equal to minus that, or really minus this is equal to that. Okay, so and you know, because of course I've only shown this for this one, but of course the same argument holds for that, and so therefore I conclude that the integral from minus infinity to infinity, taking the limit as capital R goes to infinity, of the thing I want, which is e to the minus a t plus I pi over a squared dt is equal to the integral over R of, right, so this bit here, e to the minus a x squared. Okay, so now what I will do is I will calculate that integral. Okay. All right, so let I equal the thing I want, which is integral over R e to the minus a square, x squared dx, and note that I squared is integral over R e to the minus a x squared dx times I, and I'm going to now write I in a particular way. Just change the variable of integration. And then I'm going to combine these integrals by Fubini's theorem. Like so. All right. And now what I am going to do is I'm going to integrate this over R2, not in Cartesian coordinates x, y, but in polar coordinates r and theta. Okay, so this is going to be the integral. So r will go from, little r will go from 0 to infinity, and theta goes from 0 to 2 pi. Okay, so x squared plus y squared is equal to r squared. So it's e to the minus a r squared. Okay, and then if you use x is equal to r cos theta and y is equal to r sine theta, then you can calculate that dx dy is r dr d theta. Okay, so it's r dr d theta. Okay, and so according to the convention that I use myself, this is I write it this way. And so the this one matches with this one matches with that one. Okay. All right, so now I will integrate this with a change of variable. Okay, so I'm going to use a change of variable of u is equal to r squared. Okay, and so du is du is 2r dr. Okay, all right, and then I like that because it's r dr. Okay, and so now, oh, sorry. So I am going to use that change of variable, but I'm going to actually use it after I do the integration by theta, because I can just do that directly. So this is 2 pi from 0 to infinity e to the minus a r squared r dr. Okay, so then now I'm going to use the change of variable, and so this is so sorry, just I'll go ar squared. So it's 2a r d theta. So I'm going to get an a that's going to come out now being in the denominator. So 2 pi over a, integral from 0 to infinity, e to the minus u du. And that's actually now an integral that I can do. And it's equal to 1. Oh, sorry, and I also forgot that there's going to be a 2 that's going to go with that too. So this is pi over a. So that integral is 1, and so you get, pi over a. Okay, so therefore, and remember that this is I squared. Okay, and so therefore the integral over r of e to the minus a x squared dx is the square root of that, square root pi over a. Okay, so there's that integral. And and so we go back up to our very first computation here. And what we've done now is we've calculated that that thing is root pi over a. Okay, and so CC of f is new. Sorry, just want to make sure I got the sign right there. Yeah, the sign. It's important that they're minus sign. Okay, so this is root pi over a e to the minus pi squared nu squared over a. Okay, great. So the point is the CCFT of a Gaussian is a Gaussian. Okay, so this is something interesting about the CCFT. Okay, so there's my little list of examples. Okay, then there's elementary properties of the CCFT. And I'm not going to state these. I'm just going to refer to the statements I gave for the CDFT because they're exactly the same. Okay, so we related the CCFT to the CDFT to notions of evenness, oddness, realness, imaginariness, understanding that these are not actually English words. Conjugation, transposition, and shift. Okay, and so the same statements hold for the CCFT. Okay. And so the precise statements, if you ever want to look them up, are in the course text and also in the slides that I've made available. Good. Okay, now interesting properties of the CCFT. Okay. All right. So for the CDFT, remember that we had that the codomain was little c0, right? So might it be that this is big C0, because we're now talking about not discrete but continuous time signals, and that should mean I should put a 0 up there to match the notation we used when we talked about our signal spaces. And so this was the little C0 setting was the Riemann-Lebesgue lemma for the CDFT, and so there is a Riemann-Lebesgue lemma for the CCFT, and it does indeed tell you that the CCFT is of something in L1 is a continuous signal that decays to 0 at infinity. Okay, so Riemann-Lebesgue for CCFT. All right, so the result is simply that if F is in L1, which is the natural domain of the CCFT, then FCC of F is in C0, 0. Okay, so continuous signals that decay to 0 at infinity. Right. Okay, and in fact, the signals are not just continuous actually, but they're uniformly continuous, it turns out. Okay, and that has consequences for things like inversion formulae, because you're going to get results that are going to hold not for continuous signals like for the CDFT, but for uniformly continuous signals. Okay. All right. All right, so the next class of results that we're going to look at that mirror those for the CDFT pertain to differentiation in the CCFT. Okay, now remember that for the CDFT, more differentiability of a signal meant that the CDFT decayed more quickly. Okay, and so we're going to see that a similar thing holds for the CCFT, but for the CCFT, we also, because our frequency domain is continuous, okay, we can also think about regularity of the frequency signal. Okay, and so there's regularity going in both directions. There's regularity in time and regularity in frequency, and there's rate of decay in time and rate of decay in frequency. Those kind of have expected relationships, but let's go through it carefully. Okay, so first, oops. If F is in C0, and of course it has to be an L1. Excuse me. And so you'll notice here that there's some similarities that begin to show up, or sorry, differences that begin to show up. They're not substantial differences, but they're differences. And so for the CDFT, when we stated our initial differentiation result, if you look back at it, the way it was stated was that we stated that F should be continuous and periodic, and that automatically then would imply that it was an L1 per T. Okay, but things are different for the CCFT, and continuity definitely does not imply L1-ness, and so we have to additionally assume L1-ness. And we're going to see little fussy things like this show up every now and then. Okay, and we're going to Okay, so this is about differentiability. And so there's going to be some f prime. And f prime is, again, it's going to be not quite a derivative of f, but it's going to be, f is going to be the indefinite integral of f prime. Okay, so the conditions on f prime are that f prime restricted to minus t to t, so any compact interval is piecewise piecewise continuous. Okay, so continuous on the intervals sorry, I forget now whether I've defined piecewise continuity. And so if I haven't, I should say something moderately coherent here about what piecewise continuous is. And so it means continuous on a set of intervals which partition t. Okay, and so it's with many things, best illustrated by a picture. Okay, so this is minus t. So I'm going to partition t up into some intervals like so. All right, and on each of these intervals, f is going to be continuous. Okay. And that's not quite enough. And the limits at the endpoints of the intervals exist. Okay, so I cannot have, so let me draw in red something I cannot have. So I cannot have a situation where so I partition up like so. I cannot have my function blowing up at the endpoints like that. Okay. All right, so this is piecewise continuous. This is not. Okay, good. So sorry, maybe I defined piecewise continuous before, but in case I didn't, let that serve as my definition of piecewise continuity. All right. Okay, f prime has only finitely many discontinuities. F prime is in L1. Okay, so this is very analogous to something I had in for the CDFT. But here I need to assume that f prime is in L1 because, again, piecewise continuous does not imply L1. Okay, and then finally I have the relationship between f prime and f, which is that f of t is equal to f of 0 plus integral from 0 to t prime of tau d tau. Okay, that's true for all t. Okay, all right, so f, in other words, what this says is that f is the indefinite integral of something, which you should think of as being like the derivative of f, and this derivative has to have some properties that I state here. Okay, so if all of that is true, then you get a formula that relates the CCFT of f prime and that of f. Okay, so f CC of f prime of nu is equal to 2 pi I nu f CC of f. Okay, and so the conclusion here is just like it was for the CDFT. And so the idea is, I know that f prime, the CCFT of f prime, because f prime is in L1, the CCFT of f prime must go to 0 as nu goes to infinity. Okay, and so it means that this must go to 0 as nu goes to infinity, which means that this has to go to 0 faster than nu if f admits something that looks like a derivative f prime. Okay. All right. And so by induction. And so the proof of this goes rather similarly to the proof of the result for the CDFT. And so by induction, you can increase the differentiability of f. Okay. And so if f is in CR minus 1, okay, L1. Okay, and so here's some non-negative integer, and if there exists an FR from R into C such that, okay. All right, so let me, okay, so, all right, so FR is piecewise continuous on minus t to t for every t, just as above. Okay. All right, so I think I forgot to say here, this has to be true for every t. Okay. All right, so FR has finitely many discontinuities. Okay, Fj is in L1. And this is true for every j. Okay. All right, and so, all right, so FR is this thing that I'm hypothesizing, okay, and F0, F1, all the way up to FR minus 1 makes sense because F is assumed to be R minus 1 times continuously differentiable, okay? So these are just the derivatives for 0, 1 up to R minus 1, and then for J equals R, it's this thing that I'm assuming. Okay, and then finally, F, the R minus 1 derivative of F is F R minus 1 at 0 plus the integral of the supposed Rth derivative. Okay, so it's basically the same statement as this, as the previous case, but for higher derivatives. Okay, so then FCC of FR of nu is 2 pi I nu to the R FCC of F. Okay, and just like for the CDFT, you get this conclusion that more differentiability means faster rate of decay. Okay. So we can then make the following statements about regularity of F and rate of decay of its CCFT. Okay, so the most basic one, so it's kind of the least regular F, at least for normal signals. You can talk about less regular things by talking about Fourier transforms for distributions, and we will do that later. But in this context, we're just talking about regular signals, and so the least regular thing is L1. Then what do you know? You know that the limit of the CCFT as t goes to plus or minus infinity is 0. We know more than that. We know that it's continuous also, that this is a continuous function of frequency, but I'm only interested in these rate of decay assertions here. Okay, so then what's the next most regular case after the least regular case? Well, you know, you have to kind of interpret this in the right way, but L2 is sort of regarded as being more regular than L1. Okay, and although we haven't talked about this, and this we also did this for the CDFT, we haven't talked about L2 for the CCFT yet, and we will. But the point is that in this case, FCC of F is also in L2. Okay, now you have to be a little careful about interpreting this as a rate of decay. Okay, and the reason is this: for discrete signals, being in little L2 has definite interpretations in terms of rate of decay. You know, 1 over j or 1 over n goes to 0 as n goes to infinity in such a way that the sequence is in L2, little L2, but 1 over root n does not. Okay. But the connection between rate of decay and L2 versus L1 is more complicated. And the reason is that, for example, you can have continuous signals in L2 that don't even go to 0 as, well, in this case, frequency or time goes to infinity. Okay. And so you have to sort of think of this as being rate of decay condition with some caveats, right? And so it seems contradictory, and it is contradictory in some ways, to say that this rate of decay is faster than this rate of decay, because this rate of decay at least goes to 0 This is not T, but nu. Oops. Sorry. Okay, so this at least goes to 0 as frequency goes to 0, and this may not. So, you know, there's a bit of stuff going on in the background here that we're not going to spell out explicitly, but exactly what it means, how you should think of rate of decay here as, you know, in some sense being faster than here. Okay, and it's really kind of in an integral sense. Okay. So if F is in CR, so R times continuously differentiable, and if Fj is in a 1 for J then you get a rate of decay like limit, it's nu goes to infinity, nu to the j, cc of f nu is equal to 0 for j. Okay. And then if f is c infinity, and if all derivatives of f are in L1, okay, so you might wonder whether, you know, one of these, so if, you know, let's say F5 is in L1, does that imply that already that F is in L1? Well, there are implications like that you can make, but let's not do that here. Okay. So, you know, basically in the case when R is equal to infinity, then you get the result for all R's. Okay, and so the point is that more regularity, which is kind of what's happening here, gives you faster decay of the transform. That's the punchline to that discussion. Okay. All right. So now let's look at the kind of opposite type question, which is about rate of decay of the signal versus regularity of the transform. Okay, and the result here looks a little bit different. And so let me write it down and then we'll chat about what that means. Okay. So if t goes to t to the j, f of t is in L1 for j going from 0 up to, let's say, some k, then the CCFT of f is k times continuously differentiable. And moreover, okay, there's a formula for the kth derivative of the CCFT. And so FCC of f, kth derivative of that is equal to interval. Okay. Like so. Okay. So this formula isn't surprising, because really how it comes about is that you take the formula for the CCFT, which is this one, and you just differentiate with respect to nu. Okay, so and you just wince and close your eyes and pull the derivative with respect to nu inside the integral, and you get that formula that I had there. And so the hypotheses of the proposition are the hypotheses which ensure that you can switch the derivative in the integral. So you can take the integral outside and pull it inside. And so that's where this factor of minus 2 pi I t to the k comes from. Okay. So if you're working with a signal with compact support, then it immediately follows that all of these things are going to be in L1, okay, for every J, okay, and so therefore you can conclude that the CCFT is infinitely differentiable. Okay. Good. Let's look at some examples that illustrate the interplay of these results. Okay. All right. So okay, so let's take an integer k and define a function like this, right? So it has even powers of k, so prevents the denominator from blowing up. And so this will always be in L1 because 1 over 1 plus t squared is in L1. And the reason 1 over 1 plus t squared is in L1 is, kind of because it goes to 0, like, in terms of series, like 1 over n squared. So you can use the integral test to prove that if the series sum 1 over n squared converges, then the integral 1 over 1 plus t squared will also converge, okay? Or you can just calculate the integral. Okay, good. So let's do some computations here, okay? So can show that f, the rth derivative of f, has the form, a form as follows. So it's p r of t over 1 plus t to the 2k minus r minus 1, okay? And what's pk? So pk is a homogeneous polynomial of degree to k minus 1 times r. Okay, so you can just prove that by induction. Okay. All right, and so we can conclude then okay that f r decays like that as t goes to infinity. Okay, and so where am I getting that from? I'm getting that from the denominator here. So I have a rate of decay for the denominator, and I also have a rate of decay for the numerator, and so I'm just subtracting those. Okay. Okay, and so therefore, I have that f, the rth derivative of f, is in L1 if and only if. Okay. Minus 2k minus r is less than or equal to minus 2. Okay, so it has to decay faster than 1 over t squared. Okay, and so this implies that r is greater than or equal to 2, 1 minus k. All right. Okay. And so therefore, we can conclude from this that okay, so notice that this holds for, because what do I, k here is positive integer. Okay, and so this is as k gets larger, this is only going to get smaller, and so the point is that this holds for every r in okay, and so what I can conclude from that is that the CCFT of f is infinitely differentiable. Oh, sorry, I'm doing the opposite thing here. I can conclude that the limit as nu goes to infinity, sorry, infinity nu to the r, cc of f nu is equal to 0 for every r. Okay. All right, so the CCFT of f decays faster than any power of nu. Okay. Right, and that's true for any k. All right, now what about the opposite way of doing things? So this is giving us differentiability of f gives rate of decay of the CCFT. What about rate of decay of f versus differentiability of the CCFT? Okay, so also note that t maps to t, and so so here I need to check the integrability of that thing, okay, in order to get differentiability of the CCFT, right? So t maps to t to the r, f of t is in L1 if and only if okay, And so I need to have that R minus 2K. Okay, so where does R minus 2K come from? So R comes from here, and 2K comes from here. Oh, sorry, apologies. 2K comes from here. Okay, and the rate of decay of this has to be at least 1 over t squared. So this should be less than or equal to minus 2. And so this implies that R has to be less than or equal to 2K minus 1. All right. Okay, and so therefore we can conclude that FCC of F is C to the 2K minus 1 of RC. Okay. And so in particular, when K is equal to 1, okay, so that'll just be 1 over t squared, okay, then this is just C0. Right? And so it gets more regular as K gets larger, okay, because as K gets larger, this thing decays faster, okay, and so the worst case scenario is just the C0 case when K is equal to 1, all right? So that's an example that illustrates both of the phenomenon, the interplay between regularity of the function versus rate of decay of the CCFT, and rate of decay of the function versus regularity of the CCFT. And so I should say here, again, just like I sort of babbled on for a few minutes about how you should interpret the rate of decay of that, because it's not really rate of decay, because it doesn't decay necessarily. The same kind of thing is happening here, in that we're really not looking at rate of decay, because all we're doing is we're asking for this thing to be in L1, and it may not even go to 0. Okay, so it's not really rate of decay. It's, you know, kind of more like energy. Okay. Another example is the Gaussian that we've already looked at. Okay, so in this case, okay, so here, so F, first of all, is infinitely differentiable. So F actually, and all of its derivatives are in. So first, let me just sort of make sure F is infinitely differentiable. So we'll say that to start out with. Okay, so F and all of its derivatives are in L1. Now, why is that? Okay, well, that's because if you integrate this thing repeatedly, what you're going to do is you're going to, get some polynomial terms that appear out in front of the e to the minus at when you do the chain rule of for differentiation, and so you're going to get all the derivatives are going to be a polynomial in t times this thing. Okay, and then as t goes to infinity, you know, the exponential, even worse, the exponential squared is going to swamp out the polynomials, and so this thing's going to decay exponentially at infinity. So certainly it'll be an L1. Okay, so all derivatives are in L1, and so this implies that FCC of F decays faster than any polynomial. Okay, so it's going in the forward direction from regularity of F to rate of decay of the CCFT. So also, T maps to T to the K, F of T is in L1. for every k. Okay, and so this implies that the CCFT of F is infinitely differentiable. Okay, but we knew that already, okay, because we calculated. That the CCFT is a Gaussian. Okay, and so we know that a Gaussian decays faster than any polynomial, and it's infinitely differentiable. Okay, so that's at least consistent with the direct computation that you do with F. All right, so those are kind of the basic properties of the CCFT. So again, we've gone through this much more quickly than we did with the CDFT because many of the things are quite similar. And the same is going to be true in our next lectures where we start talking about inversion of the CCFT.